We've determined that our matrix A has orthogonal eigenvectors -1, 2, 1, -1, 1, 1, 1, 0, 1. We've checked to see that they're orthogonal. Okay, we're going to call these U1, U2, U3 just so we can call them something. And the question is, are they orthonormal? And the answer that we found was clearly not. None of these has magnitude 1. Okay, well, as I mentioned, and you can calculate it yourself, I don't have to explain how to calculate this. The magnitude of U1 is the square root of 6, the magnitude of U2 is the square root of 3, and the magnitude of U3 is the square root of 2. Boy, that looks a lot like a 6. It is a 2, but now it's a better 2. Okay? So you can verify that very easily. Well, since these are orthogonal, they're still going to be orthogonal if we multiply each of them by some number. Doesn't change their direction, doesn't change the fact that they're orthogonal to one another unless we multiply by 0, and of course we know better than that. So the set U1 over magnitude of U1, U2 over magnitude of U2, U3 over magnitude of U3 has to be orthonormal. Again, U1, U2, and U3 are orthogonal, so that these are still going to be orthogonal, but now we've divided each vector by its magnitude, so now we get a vector of magnitude 1. Well, it's very easy to divide this vector by the square root of 6. Now, 1 over the square root of 6 is the square root of 6 over 6. Make sure you understand how to rationalize square roots, because you're going to be seeing it a lot. But if we do that, -1 over the square root of 6 is negative square root of 6 over 6. 2 over the square root of 6, well, that's 2 times 1 over the square root of 6, which is 2 times the square root of 6 over 6, which is the square root of 6 over 3. And 1 over the square root of 6, again, is square root of 6 over 6. Now, I'm not going to read them all to you. You can do these divisions. You learn how to do this in Algebra 1. So, you know how to divide by square root and rationalize it. Okay. So there we have it. Now the question is, have we come full circle? Remember that we started with an orthonormal set. Let's come back here. Okay. Oh man, I gotta do something about that cord. Okay. We started with an orthonormal set. And you probably can't see the extreme there, but it's the set of vectors in this matrix. We picked 3 numbers as our eigenvalues. And we talked about what it means to do multiplication by this matrix in the orthonormal basis, in the basis consisting of these 3 vectors. And we then transformed this transformation down into the standard basis and got the matrix that we've been analyzing. And from this matrix, we concluded that we have these 3 eigenvectors with eigenvalues. Now they're in the same order they were here. So the eigenvalue here is -3. Eigenvalue here is 1. The eigenvalue here is 2. Okay, well, are these 3 vectors identical to these 3 vectors? You have to look at them for a minute. Well, you see that, yeah, they are, but they're in a different order. Okay? Does that make any difference? Well, not if they have the same eigenvalues. Well, the eigenvalue of the square root of 2 over 2, 0 square root of 2 over 2 vector was 2, right? Well, right here's that vector, and it's got an eigenvalue of 2. Okay, this vector, the negative square root of 6 over 6, etc. Well, that's this vector. Now over here, this being the second vector, it had eigenvalue -3. Well, look at this. This vector has the eigenvalue. This is a vector we got for eigenvalue -3. And this is a vector we got for eigenvalue 1, and of course, the eigenvalue 1 corresponds to the same vector over here. So I've mixed up the order. If I wanted to put these in this order, I could do it. I just have to change the order of the numbers on the diagonal to match the order of the vectors. Now I would get the same transformation. I'd end up with the same symmetric matrix. Okay, well, what we've seen from this process is that if we have an orthonormal set and 3 eigenvectors, we can find our symmetric matrix, and that's actually a pretty easy process. Doesn't mean it's not a little tedious if we're trying to do it all by hand, but it's not difficult. Difficult to get it all right, as I can witness. But then, if we just then ignore this, and you need to know this because I'm probably going to do this to you on a test, and I'm probably going to ask you on the final test to go through such a process with some orthonormal set and some set of eigenvalues. So, and see that the whole thing comes full circle. Okay, in other words, just mimic what I did here. Now, if we take our matrix A, our symmetric matrix, and find its eigenvalues and eigenvectors, as we've done here. Okay, first of all, we've seen how our symmetric matrix does give us orthogonal eigenvectors. We did these eigenvectors in good faith. We didn't have any assumptions. We just did the process, and we found that the eigenvectors are orthogonal. Okay? Then we found that we could divide each of these vectors by its magnitude to get an orthonormal set. And we verified that these were orthonormal. And then we can match up the eigenvalues with the eigenvectors, and we see that we've just come back to the eigenvalues and eigenvectors that we started from. Okay? Doesn't matter what order we put these in, as long as we match the same eigenvalues with the same vectors, so that whatever order these are in, we match the order by putting our eigenvalues in an analogous order on the corresponding order on the diagonal matrix. So we have it. Now the process from here to here would be a diagonalization process. And of course, having obtained these eigenvalues and eigenvectors, we know that the diagonal matrix is -3, 1, 2 with zeros everywhere else. When the eigenvectors are in the above order. Not sure I got that last word in there. I think I made it, and hopefully you can see it. Okay, when the eigenvectors are in this order, there's our matrix. If the eigenvectors are in this order, well, you just have to, again, match up the eigenvalue with the eigenvector, get them in the right order. So had I started with this and this matrix and done the whole process, I would have ended up with all the same results. Okay, now from here to here is your diagonalization. This column of eigenvectors matrix relates the orthonormal basis representation to the standard basis representation in a way that hopefully you understand. You want to work through this process because it embodies a whole lot of everything we've learned in this course and is kind of a culmination. Now I'm going to go on and talk a little bit about why we do what we do when we do the eigenvectors, just as a little review, because you need to know this. And then I'm going to prove that, going to show you why, I'm going to prove that no matter what the dimension of the space, if we have an orthonormal set of eigenvectors, and do this process, we're going to end up with a symmetric matrix.